Final quadrilateral. We've been talking about parallelograms and rectangles and rhombuses, and now we're getting to a square. And a square has the most properties. It's the most specific of all our quadrilaterals. So the first exercise, well, the definition first off, a quadrilateral with 4 right angles and 4 sides of equal length. So in exercise 1, based on the definition above, the square is which of the following type of special quadrilaterals? So we're looking to see if it falls under the umbrella of those other ones. And for a rectangle, it does because it contains 4 right angles. That's all that's required to be a rectangle. For a rhombus, yes, because it contains 4 equal sides, which is the only requirement for a rhombus. Parallelogram, square has opposite sides parallel, so we're good there. And a trapezoid, square has at least one side parallel, so we're good there as well. So it falls under all of the umbrellas, and that puts it as the most specific of the quadrilaterals. Squares have so many properties and uses in the real world, so we'll look at a few of those here. First off, Kimmy is designing a square garden. Diagonal is exactly 16 feet long. She wants to put some perimeter fencing around it, and if the fencing she likes comes in 12-foot rolls, how many rolls will she need? So I've drawn a square here with equal side lengths because that's what a square does. I've got the diagonal drawn in 16. And you might be asking yourself, why doesn't she just measure the edges? Perhaps she only has the diagonal measured out and doesn't really want to trace out the square just yet. But whatever reason, this is what we're looking for. So we need to solve for that outer segment. So we set up Pythagorean theorem on both of these triangles. We've got x squared plus another x squared equals our diagonal squared. And you can see how the rest of the equation solves out down to 11.3. That's just one side length though, so the perimeter is going to be 4 of those sides, and if we need to buy this in 12-foot long rolls, we're going to need 4 complete rolls. There will be 2.8 feet left over. So that is our first calculation. In exercise 3, the diagram here is showing a square with outer square with a possible inner square, and that's what we're trying to explain, whether the inner quadrilateral is also a square. So looking at that outer square, if it's defined to be that, then all of those segments will in fact be equal. And with E, F, G, and H also being given as midpoints, then all of these triangles on the outer side would have to be isosceles because these are segments that are formed by midpoints on already equal sides. So AHE and BEF and FCG and DGH, those are all isosceles right triangles. Given that, any isosceles right triangle is going to have a couple of 45-degree angles in it. If we put a pair of 45-degree angles on that straight line, it's going to leave 90 in between. And so that's the first criteria for that being a square, is that we have 4 90-degree angles. So that's been proven. The other thing we need to prove is that all 4 sides are the same length. So when you look at those isosceles right triangles, if we can show that they're congruent to each other, then all of their hypotenuses will also have to be equal. So the way we show that is to say we have a side angle side relationship among them, being that these half segments are equal to each other all the way around, and being that they all contain a right angle, we can make that argument. So that leads to corresponding parts, these hypotenuses also being equal all the way around. So if we take the midpoints of a square and connect them, we'll get another square. That's the summary there. This next section here, we're looking at a quadrilateral on a grid, trying to prove that it's a square. And so we just go through the same calculations that we have in the past, using distance formula to show that they're the same lengths, and using slopes, whether we do it with coordinates or rise over run on the grid, to show that they're in fact perpendicular. And you can pause and take a minute to write that down, but that's the same type of calculation we've done in the past with coordinate grids. And finally, this last section is one that you should definitely pause and try on your own before we get into the explanation. But basically what's happening here is a set of conditions is given to you, and you have to figure out whether that's enough to say that it's a square. So think about each piece and decide whether that may be enough. Try it on your own, and then we'll talk about them. All right, so if we have a quadrilateral with 4 equal sides and 1 right angle, would that guarantee a square? And so first off, the 4 equal sides does guarantee a rhombus, which is a type of parallelogram. And if all consecutive angles in a rhombus are supplementary, and one of them is 90, then they're all going to be 90 as you move around the parallelogram. So that would be enough information if we take it with what all the properties lead to. So yes, a quadrilateral with 4 equal sides and 1 right angle must be a square. If we have a parallelogram with equal diagonals and 2 adjacent sides of equal length, would we have a square? Well, looking at that, a parallelogram with equal diagonals has to be a rectangle. That's one property of rectangles, is that when we have equal diagonals, we must have a rectangle. So the opposite sides are congruent, and if the adjacent sides are also congruent, then all 4 sides are congruent, and we will have a square there as well. So a parallelogram automatically has opposite sides congruent. If we also say that the adjacent sides are equal length, that makes all 4 sides equal, in addition to the 90-degree angles we got from showing that it's a rectangle. All right, part C, a parallelogram with perpendicular equal diagonals. Perpendicular diagonals guarantee that it's a rhombus, and a rhombus would then therefore have equal sides. And the equal diagonals guarantee a rectangle, which would guarantee the 4 right angles. So yes, if we have perpendicular and equal diagonals, we will have, in fact, a square. And finally, a quadrilateral whose diagonals are perpendicular bisectors of one another and 1 right angle. So being perpendicular bisectors guarantee that it's a rhombus, because we would have as soon as we get perpendicular diagonals of any kind, that's showing that it's a rhombus. Being that it's a bisector would actually rule out a kite as a possibility. The kite is not a figure that we've discussed very much, but that would have been a possibility with just perpendicular. So we do need the bisector in there. And so that shows us that all 4 sides are equal. With consecutive angles being supplementary, that would give us the 90-degree angle. So we know that once we know that it's a rhombus, all the parallelogram properties come in. Therefore, all the angles are supplementary as we move around it. And if we have 1 right angle, we would then have all right angles. So the rhombus would have right angles and therefore be a square.